Hi everyone, my name is Sandeepan Halder and I and two of my friends Arijit and Pratyasha, we are final year undergraduate students from Mechanical Engineering Department. We have taken the problem statement of weight optimization of helical spring um, as our assignment submission for the course AI 61005 of IIT Kharagpur. So helical spring are present in every aspect of mechanical engineering. So optimizing its design has a very significant engineering interest. Minimizing the weight of the helical spring will reduce the manufacturing cost as well as the waste of materials. So we are trying to implement the paper, this paper, which is optimal design of automatic suspension springs using differential evolution algorithm. Mm. Just for the quick introduction of this paper, uh, so the objective function in the objective optimization of the spring, the minimum weight or the minimum volume is taken as the objective function. So here the objective function is taken as the minimization of the mass of the spring, and it is calculated by this following equation. We will come to the variables one by one. So first let's come to the design variables. Design variables are the capital D, the small d and the n. So capital D represents the spring diameter, small d is the wire diameter, and n is the number of spirals present in the spring. Now each of these variable has a specific domain which is shown in this table here. For example, the spring diameter has a lower limit of 80 millimeter and upper limit of 89 millimeter, so on and so forth. Uh, now let's come to the design parameters. So the modulus of rigidity of the material has been given as 7,800 kg per meter cube. The load is 85.2 into 10 to the power 3 megapascal. And finally, the Q, which is present in the objective function, the Q is the quantity of inactive turns, which is 4,600. There are some additional constraint. So the initial constraint is the maximum shear stress present in the coil, and this shear stress occurs in the inner face. The formula is given. This all has been implemented in the code itself. And the second constraint is the maximum deflection, which is represented by delta. The side constraint that has been used for tau and delta are respectively 250 to 200 and 22 to 50. So we will implement these functions various iterations of genetic algorithm and simulated annealing. My friends will describe this process further.
Hi, I'm Arijit. I'll be talking about the genetic algorithm part of our problem statement. Uh, in our problem, there are three variables, capital D, small d, and n, whose domains are mentioned here. These are the design parameters, design constants. Now, let's move on to the fitness function first. Given the current state S, which is a tuple of capital D, small d, and n, we first calculate the mass, the thing which you have to minimize first. We also calculate two other things, tau and def. Tau is the maximum deviation, maximum shear stress allowed, and def is the maximum deviation allowed. If either of these two is found to be violating the maximum limits or minimum limits, we add a heavy penalty to the current fitness. This ensures that this state is very quickly subsequently dropped out in the future generations. Now, genetic algorithm has three main parts: selection, crossover, and mutation. We'll talk about this one by one. Now first, let's look at the implementation first. This is the constructor. There are 6 hyperparameters: the number of iterations, the population size, the mutation probability. Now the elite ratio. Here the elite ratio is 1%. It means that the 1%, the top 1% fitness values in the ith generation will directly move on to the I plus 1th generation. Parent portion means that 30% of the ith generation will move on to the I plus 1th generation. Now the difference between elite ratio and parent portion, which here is 29%, will be randomly selected from the ith generation. Let's look at the crossover function. Here we are implementing uniform crossover, which means that given two states x and y with uniform probability we are swapping each of the variables in the states. And now let's look at the mutation function. The mutation function means that given a state x, we are randomly shuffling a given attribute between the maximum and minimum bounds of the given variable. Let's look at the run function. We are first initializing the population array randomly. The population array is such that the number of columns is one more than the number of variables, because in the last column we are storing the fitness value of the individual. Now in each iteration, we are sorting the population array by its fitness value, so that the person with the least fitness, because here we are minimizing the fitness, is indexed first. Now we are calculating a probability array such that the person with the smaller fitness has a greater chance of continuing in the next generation. Here three types of selections are happening. Now let's look at them. First, elite number of people are automatically selected from the ith generation. Next, a few individuals from the ith generation with the weighted probability distribution calculated here are randomly selected. After selecting the people who will move over from the ith generation, we are further from selecting a few individuals from them who will act as parents and mate to form offsprings. So here we are calculating the required number of offsprings by mating the parents, and now after the formation we are giving them a chance to mutate, and we are appending them for the population array of the i+1th generation. After all the iterations have been completed, we are finding the global maxima, and now we are displaying the result in form of a plot here, and the optimal values of the parameters for the best fitness function, which also satisfy these given constraints.
Hello, let us move on to solving the spring design problem using simulated annealing method. First of all, let us look at the basic overview of the method. We have the neighbor function, which is just a function that takes in a state and returns a random new state after doing some transformation to the previous state. An important property of the neighbor function is that it doesn't change the answer by too much. Then we have the temperature function, which decides how willing the algorithm will be to move to a worse state. In other words, if temperature is 0, we'd only move to better states, but if the temperature is infinity, we'll move to any state regardless of how good or bad it is. At the crux of simulated annealing, we have acceptance probability function, which determines the probability of going from one state to a neighbor state, and it is dependent on the temperature function. So let us look at our state. Our state consists of the spring diameter, which should be between 80 and 89, the wire diameter, which should be between 14 and 21, and the quantity of active spirals, which should be between 5 and 9. We are given the rho, g, f, and q values. Domains refer to the range within which each of the variables must reside. First of all, we will so here these are some of the functions. The rand init function will initialize the state randomly, and the scale function will scale this random number, which is between 0 and 1, to the particular domain that we have mentioned for a particular variable. The objective function will give us the value of the objective for a particular state. Now we will check if a particular state is valid or not. For that, for example, we have the tau value. The tau value should be between tau max and tau min. Similarly, the dev value should be between dev max and dev min. If all these constraints are satisfied, then we return 1, otherwise we return 0. Then we have the neighbor function. In this neighbor function, we take one of the variables randomly and we change its value, keeping the other values constant. So that is how we generate a random neighbor of a particular state. Here we also check if the new neighbor generated is valid. We will continue this loop till we obtain a valid neighbor. We initialize the temperature to 100 and we will continue the loop till the final temperature is 0.01. Delta T is the value which we multiply to the temperature every time to obtain our new temperature. First of all, we initialize the state, and current value, curval is the current value, and that is the value of the objective function for state S. Best value will be equal to the current value, and the best S will be the current state S. We will store the iteration. We will store the number of iterations and the costs. So here we will obtain the neighbor for a state S. So S1 is the neighbor for state S. Then we obtain the value of the objective function at state S. We will obtain delta E, which is the difference between new value and the current value. In case the new state is better than the previous state, we have delta E less than 0. So in that case, we do the updates, and if best value up till now is worse than the new value, then we will update the best value and the best S as well. But in case the new state is worse than the current state, current best state, if the new state is worse than the current state, then we will move to that state depending on the acceptance function. So we calculate the acceptance function, which is this p value, and that is e to the power minus delta E by t. So as temperature increases, the value of the acceptance function increases. That is, we will have more probability of acceptance. And in case and then we obtain a random number. In case that random number is less than this probability value, then we will do the updates, otherwise we will do nothing. And here after each iteration we will update t, that is we multiply t by delta T, which is 0.99 in our case. We will append the best costs up till now, and we will append the number of iterations. We will plot the graph, and here as we see at the beginning of our iterations we have such a high value, that is around 5.6, and it gets reduced to 4.076. So it gets reduced to 4.076 after a number of iterations. So finally we obtain the capital D value, which is 80.17, the small d value 17.13, and n value 6. So the best value of the objective function is found to be 4.076. So that is all for simulated annealing method.